This is the first part of lecture 6 on wideband channel modeling, and lecture 6 is the last lecture in the lecture series on channel modeling. This lecture series included lecture 2, which was Introduction to Channel Modeling, lecture 3, which was Narrowband Channel Modeling, which is basically path loss and coverage and variations of the channel, lecture 5, which was measurement techniques used for measurement of wideband characteristics of the channel, and this is the finale lecture, which is now wideband channel models and the way that they are treated in the standards. Now, in here, I have like a bunch of numbers in here, 6.1 to 6.8. These are actually sections of the new book. And I will cover most of the sections, and I have divided them in parts. But my emphasis on different parts are different. Most of my emphasis is in the first part, section 6.1 and 6.2. And then I will cover 6.3 to 6.8 very briefly, but I give you only the essence of that because there are like some mathematics involved in part of these material. All of these guys, they have separate mathematics. So you have a lot of math equations and things related to that. But application of those things are very specific whenever you want to use them, and they are very simple to be used sometimes. But these material are the common material. Most of the channel modeling activities today are the time domain statistical models in the standards. So as a result, most of my emphasis are in these two parts. 6.1, which is introduction, and actually 6.2. This is the most important chapter in terms of like learning the details. And after that, it's good to know about them, that they exist, that if in certain time you want to go to them, you can go to them. So I provide you an overview of that. To start with, I have taken this channel modeling, broadband channel modeling, similar to measurement system. I have divided them to wideband time domain statistical model and frequency domain models. And then I have another division. These are the two together are called statistical models. Then I have building a specific like ray tracing or direct solution of radio propagation equations. So this is another category that we call it building specific or site specific. Basically, that's a way that we try to solve propagation equations somehow. Either Maxwell's equations or using ray tracing, which is an approximation, optical approximation to Maxwell's equations. Now, then I have one last part in there, which I call it a site-specific statistical model, which is a combination of statistical modeling and information about the site. See, when we are talking about channel modeling, in particular in this course, my emphasis is on indoor. So you can have the map of the building, you cannot have the map of the building. It makes a lot of difference. Traditionally, in the standardization activities, they are focusing on non-site specific things. Okay? But if you want to go, buildings have so much of variety that site-specific things, like ray tracing, for example, are more accurate. And then this site-specific statistical models is something that I think is a good area for like future in this field, which has a combination of building a specification, but is not mathematically as cumbersome as ray tracing. In general, statistical models, which are based on channel measurement, are simple to be applied. Ray tracing is a more complex software. Okay, with that introduction, about techniques for modeling, let me just start and tell you that what is modeling in fact, and what do we want to model. Basically, you remember I had this figure before. If you have like a base station in here and you have a terminal which is moving away from the base station, power starts to fluctuate and go down. If you remember, these fluctuations was the so-called what? Rayleigh fading. And then the power drop was according to the distance power path loss model. And then on top of that, variations of the average power from the distance power path loss model was the so-called shadow fading. These are the things that we studied from this figure when we were talking about narrowband modeling. Okay, so when we were doing narrowband modeling, we attributed 3-4 statistics to these variations of the channel. And at the end, what we said was that, okay, when this channel is changing, Fourier transform of these changes is a so-called Doppler spectrum. And this is something that I will keep in mind. And we learned how to simulate it actually in chapter 4. And we had a project on that. Then another thing that we did was we came and we said that if you take these points and you take the statistics of this point, you are ending up to Rayleigh fading. And that Rayleigh fading is the one that you use for calculation of probability of error when we talk about modem design technologies later on. Okay? And then we had path loss model, which we use the path loss model for calculation of coverage. And shadow fading also for calculation of the coverage. But when I have the shadow fading, I can do the calculation of the coverage with fading margin. Okay, which gives you the probability, it gives you the allowance to calculate the coverage with the probability of coverage. Okay. Now, what do we do in wideband modeling now? Basically, we take, in the narrowband models, we just learn that if we have one single path, we do like Jake's model or like a JTC model. We put a filter, we run it with this, and that gives you variation of the amplitude or the power. I can reproduce this variation of amplitude for received signal. Now, in wideband, really, what they do in wideband modeling, what they do is that they take that from one path and they repeat it for several other paths. So basically, that narrowband modeling or simulation that I had earlier is just expanded here, in a sense. But before we go to the detail of those things, let me just tell you that what is happening really in broadband or in wideband modeling. What is happening is that when I'm like close to the transmitter, if I take one of these like points in here, and at that point, very quickly, I measure the impulse response, similar to the impulse responses that we had in project number 2. Okay? So I get something like this. Since I'm close to the antenna, I have one strong path, which is direct path, and some little paths coming from reflections. As I go away from the base station, these paths getting more spreaded, and the strongest path comes weaker. Okay, so it becomes gradually weaker. Remember, each of these multipaths are associated to one of these points. And in each point, this is total power, which is sum of a square of all of these paths. Okay, this is what I see in here, the variations. Now, I look in this point, I go further, first path gets weaker, I go further, it gets weaker. But as first path gets weaker, I have other paths which are becoming stronger. Okay, so they become, and finally at certain stages, actually first path may die. I may not be able to detect it. And still I have a bunch of spreaded paths coming from other places. This is what is happening. And I want to model that. When I want to model this, modeling is always for an application. There is an objective to model. In engineering, that's what we do. Okay. Now, we will talk about the objectives a little bit later, but there are three different type of people who are interested in these paths. But anyways, what I do then, I'm close to, and I go away and I collect a bunch of multipath profiles. And I want to see these multipath profiles, which are taken at different times and different spaces, how I can reproduce them. That's the modeling. How they behave, that's the understanding. Okay. But basically, as we saw earlier, each of these things are not really like an impulse. When you see them, I mean the measurements, like the measurements that you had in your examples, like they are something like this, like this. These are the actual measurements. Because if I have impulses, my bandwidth is infinity. Okay? But I never have infinite bandwidth. So I have a pulse, which is like, if my bandwidth is whatever, it would be like a sink that this area is inverse of the bandwidth. Okay? So as a result, these pulses, they look like this. For example, in your your project 2, the bandwidth was 200 megahertz, so this width was like 5 nanosecond. Okay? And you were seeing things like that, or like this, rather than in these impulses. So what I'm doing actually in here, especially in first part of my lecture, I'm talking about a statistical channel modeling. What is the meaning of that? Meaning is that I collect a bunch of these impulses, impulse responses like this. I collect a bunch of these impulse responses, then I want to develop a model. Very similar to what samples that I had in my projects. Okay. So I don't know the location. So what do I do with these things really, with these measurements? And how do I measure them? I showed it in chapter 5. I have different measurement systems. The most complex measurement system was what? The one which does two-dimensional measurement. Means that angle of arrival plus arrival of the path. So basically in measurement, as I move, impulse response changes in different locations. And I have a bunch of these impulse responses. And what I want to do is that I want to develop some models. First thing that I have to do is I take these impulse responses and I extract some parameters from them. What are those parameters? This is a typical measurement. This is a two-dimensional measurement that was done by Bob Tingley, one of my PhD students in his PhD program. And around the year 2000, that was when he published this. And this is a two-dimensional measurement of the channel. In here I have phase. In here I have delay of arrival. So this is tau, and this is what? This is like phi, we call it. Sorry, I mean in the things I have called it theta actually. Angle of arrival, theta. Okay, you remember that each of these paths that I have in here, associated to this path, I have an amplitude, which is beta. I have a delay of arrival. If it is tau, this is the delay of arrival. This is delay. That's tau. Okay? Then I have a phase associated to this guy, which is the phase of the thing that I call it phi. And also I have a theta, which is angle of arrival, which is this thing. This is the theta, angle of arrival. So if I have like a measured general two-dimensional, the best measurement, and I will extract from that a bunch of beta, phi, tau, and thetas, which are these four parameters are representing what? Are representing one path. One of these paths. For example, this path, I take this path, and then I will. Now, how do I detect it? You saw it in your previous project. What you do is that you take the sample, you find the peaks. Location of the peak is your tau, amplitude is your beta, And if it was two-dimensional, the angle was theta, okay? And there is a phase associated to that. That if it's non-coherent measurement, you can measure the theta, the phi. If it is coherent, you will, if it is non-coherent, you cannot. And you assume it's like linearly distributed random variable. And if you can measure it, means that your system is like coherent system, then you measure it and you put it in there. But anyways, associated to each path, I have 4 parameters, and I have a bunch of paths, 1 through L. These are the paths that I have. Okay? So basically, in modeling, the most general model, I have 4 parameters associated to each path. And if I want to sketch it, I end up with something like this. I end up with a 2-dimensional path, a 2-dimensional impulse response like this. This is the most general thing and most complete thing that you can get. But most of the time, my measurement systems are not so complex to measure 2-dimensional. So what I measure is really 1-dimensional. What is 1-dimensional? Means that I take all of these paths that I have in here and I map them under in here. I map them in the top because I don't have the theta. Okay, so my impulse response would be something like that. Or in another word, the relationship between these two is that in here, in this one, I take each path associated to that, I have an additional theta. Okay, which is what I see in here, in this axis. This is the theta, this is the amplitude. And when I want to go from this one to this one, basically I take all of these paths and I map them to the tau axis. Okay, which I end up to see something like this. Make sense? But in reality, people, they don't do 2-dimensional measurements because it's a very tough measurement system. Just recently people do that. It's very expensive. I mean, equipments which are used for 2-dimensional channel measurements can run up to $500,000. Actually, that's one particular one with Electrobit in Finland. They have a channel sounder which costs over $500,000 for multidimensional. The one that my student did was experimental, and he did it by hand. It was not as expensive. But the core of that was a network analyzer, and it was not very fancy. It was simple. But it was experimental at that time. But most of the people, the measurement systems that they have for the reason of cost is the simpler 2-dimensional, which is something like this, and which is the same as what you did for your project. So you have like a network analyzer, for example. You sweep the channel, you take the inverse Fourier transform, and you get something like this. And then you find the peaks and location of the peaks, and those are your taus and your betas. And then you assume these phis are uniformly distributed random variables. That's more or less how you do it. How you extract the parameters. When you extracted the parameters, then you develop models. Okay? Now, so this is the basic idea of extracting the parameters from 2D and 1D modeling, or extracting of parameters for 2D and 1D modeling out of measurements, which could be 2D or could be 1D measurements. But bottom line is modeling of the beta, phi, tau, and theta. Okay. Theta is angle of arrival. That's the toughest one, most modern one. Tau and beta are very easily calculated from the channel profile. Phi, if we don't measure it, we assume it's uniformly distributed random variable. That's a very good assumption. Very valid assumption. Okay, so with this thing, I now got the general idea of a statistical modeling. What I'm doing is that I'm going to different locations. I collect a bunch of channel profiles, 2D or 1D, and from the profiles I calculate a bunch of parameters. What are the maximum number of parameters that I have associated to each path? Is 4, but it could be 3, it could be 2. Okay, and then based on those numbers that I have collected, I will develop a statistical models. This is what we call it wideband statistical modeling. Now, to go one step further, now I want to tell you that these 4 parameters that I calculated, or I determined from the measurements, 4 were beta, phi, theta, and tau. Okay, amplitude, phase, angle of arrival, and location of arrival, of time of arrival. These are the 4 parameters that I measure from the measurement. But who is interested in this for what application? If your application, the most traditional application is for communication. In communication application, the most important parameter, if you remember, I've talked about it many times, is tau RMS, RMS delay spread, which is basically I want to know how much these paths are stretched. Okay, I want statistically how much they are spread, because I can get the excess delay, which is from here to here. That's also good parameters. But what if the first path was strong, the last one was very weak? So a measure of a spread of these multipath, a better measure is what RMS delay spread, which is second central moment, which is a sort of like RMS value, like when I'm talking about DC versus AC. That RMS is the same as this RMS. RMS is always second central moment. Okay, so this is what I need in communication applications, because this tau RMS is what inversely proportional to the data rate that I can have. And we have talked about that several times, I believe. If you inverse this tau RMS, like 10% of that is the data rate, or I mean post-transmission rate that you can have without significant intersymbol interference. Problem with multipath is that if I increase my data rate, my pulses become narrow, and if I have several coming one after another, they overlap and they cause intersymbol interference, which causes a lot of errors. And I want to avoid that. Okay, so in communication, I'm interested in tau RMS because tau RMS is related to intersymbol interference. So that's it. That's where I am in there. What about the other thing? Who else is interested in that? People who are designing like MIMO systems, for example, they are designing a bunch of antennas which are not sensitive to what angle of arrival. Because there's an antenna, and this antenna has like different sectors, spatial sectors. Okay? And then, so these paths which are arriving, I want to know which one arrives from which angle. These are the thetas. If I know which angle is arriving, then I can take this impulse response similar to the one that I had before. I can come from there and to here. Okay? And then I can analyze the system. If I have a MIMO system, basically what I do is that I take signal, I separate the signal from different angles, and I use them to improve the performance of the system. Okay? So as a result, if I have a MIMO channel, I need to know at angle of arrival in addition to the beta, phi, and theta. For communication and application, I'm interested in tau RMS, which is related to tau and beta, the two main parameters. In MIMO systems, I'm also interested in angle of arrival. Okay, so when we go to like 802.11n, which is talking about MIMO, then the channel model has theta in it. But if I go to 802.11b, which doesn't have MIMO channel, it's only these three parameters to be modeled. Okay, so this is up to here, traditional channel models. Then there is another important issue. Important issue is the issue of geolocation using time of arrival. For geolocation using time of arrival, they take the arrival of the first path, which is TAW1, and based on that, they calculate the distance between transmitter and receiver. So for geolocation systems using time of arrival, people are interested in modeling of the first path. Arrival time of the first path. So that's a third class of models. So if we go to the literature, we see three classes of models. Models for beta and tau and phi, which are like traditional communication applications. Models for theta on top of the previous one, which are models for MIMO, and modeling of arrival of the first path, which is for geolocation. Okay, so I have a bunch of measurements, and this is how people use them differently for three different purposes. And three different purposes is, one is communication, I mean traditional, and the other one is MIMO, which is more advanced communication. The third one is geolocation. Each of these guys are interested in different parameters from the multipath profile. Okay? Communication people are interested only in the arrival time and magnitude. MIMO, they are also interested in theta. Geolocation people are interested in arrival of the first path only. And strength of the first path with respect to the strongest paths after that. Because they want to know when first path get buried under other paths. Okay? So as a result, when I look at the literature, I have a bunch of channel models that I have classified them in these three categories. What I do at the beginning, in continuation of this video, which is the first video of this lecture, I'm talking about traditional communication systems. So I'm interested in the multipath profile. For the first path, I assume for these telecommunication applications, I assume that this first path is normal, always arrives at tau1 equal to 0. So I'm not even interested in that. And I'm interested in the rest of these guys, and I don't care what is the theta. Don't care. If you do that, then you're talking about traditional. This thing is the traditional channel models. Okay? And I'm talking about traditional time domain channel models. Now, what are these traditional wideband channel models? What do? They want to model this multipath profiles, their time of arrival, and their amplitudes. Now, how many models are available and how they do it? Basically, we have a bunch of models for wide area networks, like we have models for GSM, we have models for JTC, which is for PCS applications, and then I call those two in one category, which is wide area channel models. And then I have local area channel models, the models which are developed with 802.11, different branches. And I will go over those models as my examples. But before I go there, let's see that these standardization committees which are working on traditional time domain models which are used in the communication applications, these are used in traditional communications. How do they look at this? Okay, the general impulse response, as I saw in the last page, mathematically speaking, is a function of tau, which is time of arrival, and theta, which is angle of arrival. So it is beta I times time of arrival, angle of arrival, both represented by impulses. And then I have phase in here. This is the traditional 2D impulse response. For traditional communication application, I go to 1D impulse response, which neglects this part, neglects the angle of arrival. So basically, what I say impulse response is a bunch of impulses with amplitude beta I, phase tau I, and arrival time of, phase phi I, and arrival time of tau I. This is my general impulse response, which is equivalent to what? To whatever that I have in here. Okay. Now, how do we want to do the modeling? The modeling, all of these standardization examples that I give you, which is like GSM, JTC, 802.11, all of them, they use the scattering function for the modeling. If you remember, a scattering function was something that we observed in the classical radio channel modeling. And basically, we said this scattering function, if I have a slow time varying function, can be decomposed in two functions. This one, which we called it delay power spectrum, delay power spectrum, and then this one, d lambda, which was what? The Doppler spectrum. Doppler spectrum. Do you remember that? What was this Doppler spectrum? Doppler spectrum could be like this double ear thing for mobile, which was Clark's model, coming out of Clark's model. Could be uniform, which was the one that JTC was using. Could be like something like this, which is something that 802.11 uses, 802.11n uses. But there are limited number of spectrum shape for d sub lambda that we have to specify. The highest value of this thing was the so-called FM, which was related to what? The velocity, if you remember, was maximum Doppler shift, which was velocity over the speed of light, time frequency of operation. And this FM for indoor was something like 10 Hertz, for outdoor something like 100 Hertz. Now, what was Q sub tau? Q sub tau, if you have a like channel impulse response, really is magnitude square of channel impulse response. So if I have like impulse response like two paths, one of them is 2 and the other one is 4, then Q sub tau is, first one is 16, second one is 4. That's the meaning of Q sub tau. The other one is 4. Okay? So Q sub tau is basically impulse response square. If you do the impulse response square, and you can interpret it differently. If you do spatially, you have to take the average over all the betas that you have measured at that time. So a standardization activity comes there and defines two things. They give you Q sub tau, something like this, and they give you d sub lambda, which could be something like this or this or this. And meaning of that is that I have a Rayleigh random variable or a Ricean random variable with this type of spectrum. That's it. That's how traditionally communication standards define a standard. Now we can go through some examples. Now, I think for the purpose of like collecting the videos, maybe we give a pause right now for like a couple of minutes, and then we start the next video, which are the examples of traditional